Every single morning, it wakes up our world. A gentle golden sphere of warmth that has nurtured life on this fragile rock for over 4 billion years. We think we know the sun. We calculate its patterns, we predict its seasonal weather, and we treat it like a cosmic clock, constant, predictable, and comforting. We bask in its light, confident that we have mastered its nature. But if you look closer, past the blinding light, you realize our star is hiding a dark secret. A secret that defies the very laws of physics. A mystery so deeply unsettling that, for decades, it has left the smartest minds on Earth quietly terrified. Imagine walking up to a roaring campfire on a freezing winter night. As you step closer to the dancing flames, you get warmer. You can feel the heat radiating on your skin. As you back away, the cold air returns. It's common sense, it's intuitive, it's the second law of thermodynamics. Heat always flows from hot to cold, naturally dissipating as it travels outward. But now imagine stepping away from that campfire, walking 50 feet back into the dark, and suddenly bursting into flames because it is somehow 300 times hotter out there in the freezing night than it is right next to the wood. That impossible physics-breaking paradox is happening right now, right above our heads. It is the solar mystery we were never supposed to solve, and today we are going to step directly into the fire to find out what is really going on. To truly understand this cosmic crime scene, we have to examine the anatomy of our star. Deep inside the solar core, under pressures that crush hydrogen atoms together in a state of perpetual nuclear fusion, the temperature burns at an unimaginable 1.5 times 10 to the power of 7 degrees Celsius. It is here, in the heart of this atomic engine, that energy is born as high-energy gamma rays. But this energy cannot simply shine outward. The core and the surrounding radiative zone are so unimaginably dense that a newly born photon cannot travel more than a fraction of a millimeter before colliding with a free electron or a hydrogen nucleus. These particles absorb the photon only to spit it out in a completely random direction. This chaotic journey is what physicists call a random walk, or more colorfully, the drunken walk. Instead of traveling at the speed of light directly out of the sun, a single photon must stumble, bounce, and rebound through this atomic labyrinth for anywhere from 100,000 years to 200,000 years just to reach the convection zone. By the time this ancient energy finally rides the bubbling currents of superheated gas to the visible surface of the sun, the photosphere, it has lost its extreme gamma ray intensity. It cools down, emerging as visible light, and its temperature drops to a relatively cool 5,500 degrees Celsius. Still incredibly hot, yes, but entirely logical. The heat is escaping the furnace, dispersing into the freezing void of space. But then, we cross a threshold. We enter the outer atmosphere, the corona here. Millions of miles away from the nuclear core, the temperature does not continue to drop. Instead, it violently, inexplicably skyrockets. In the corona, temperatures suddenly leap to over 1 million degrees Celsius, and in some active regions up to an astonishing 3 million degrees Celsius. This is the coronal heating problem. It is the physics equivalent of throwing an ice cube into a boiling pot of water and watching the water instantly freeze. It violates the very laws of thermodynamics that govern how energy moves through the universe. For nearly a century, astrophysicists have stared at this phenomenon in sheer frustration. The math simply didn't work. The laws of thermodynamics dictate that this region of space should be cold. Yet something invisible, something of unimaginable power, was actively pumping energy directly into the sun's upper atmosphere, superheating it to temperatures hotter than the surface itself. In the 1930s, when astronomers first analyzed the light spectrum of the corona during eclipses, they detected a mysterious green spectral line that didn't match any known element on Earth. They jokingly called it coronium, believing they had discovered a brand new element. But when Swedish physicist Bengt Edlund analyzed the data, he discovered something far more shocking. It wasn't a new element. It was iron. For generations, we were locked out of the mystery. The corona is so violently hot, so choked with radiation, that any probe we dared to send to investigate would be vaporized, turned to ash before it could whisper the answer back to Earth, until we built a shield capable of touching the beast. In August of 2018, NASA did the unthinkable. They launched the Parker Solar Probe. This wasn't just another satellite, it was an engineering marvel designed to do what was long deemed impossible: touch the sun. To survive this suicide run into the dragon's mouth, engineers had to build a literal shield of Achilles. The probe is protected by a revolutionary heat shield just 11.4 centimeters thick. Made of an ultralight carbon-carbon composite foam sandwiched between two carbon fiber plates, it is designed to withstand temperatures reaching nearly 1400 degrees Celsius, but the shield itself was only half the battle. How do you keep the instruments behind it cool when they are being hammered by high-energy solar particles? To solve this, NASA engineers had to invent an entirely new kind of cooling system. Normal liquids would vaporize or freeze in the extreme environments of deep space. Instead, they designed a pressurized, closed-loop radiator system that uses deionized water under high pressure. This pressure raises the boiling point of the water, allowing it to absorb intense heat from the probe's electronics and dump it into outer space, keeping the sensitive science instruments at a comfortable 30 degrees Celsius while just inches away. The heat shield is white hot, moving at speeds of over 150 kilometers, fast enough to fly from Washington, D.C. to Tokyo in under a minute. The Parker probe plunged deeper into the solar atmosphere than any human creation in history. To reach these speeds, the probe had to execute 7 hyper-precise gravity assists around Venus. Venus was not used to speed the probe up, but rather to act as a cosmic brake, stealing some of the probe's orbital energy and allowing it to fall closer and closer to the Sun. Eventually, it crossed the Alfvén critical boundary, the invisible line where the solar wind officially becomes supersonic and the spacecraft officially enters the Sun's domain. And what it detected there sent chills down the spines of the mission controllers back on Earth. The probe didn't find a smooth burning atmosphere. Instead, it detected a chaotic, violent wasteland of magnetic anomalies that scientists call switchbacks. These are sudden, incredibly violent, S-shaped kinks in the magnetic solar wind that literally reverse the magnetic field direction by 180 degrees in a matter of seconds. When these magnetic loops bend, stretch, and violently snap back into place, they release a whiplash of pure energy. Imagine a giant magnetic rubber band stretched to its absolute limit, suddenly snapping.